So yeah, as you said, I'm a PhD student at the University of Oslo in Norway, and I'm part of Big Insight, which is a center for research-based innovation, which means that we are partly funded by the Norwegian Research Council and a lot of private companies in Norway. And we try to tackle research problems that are interesting both from academic viewpoint, but also from interesting for the industry. And in the later years, they have started to use more machine learning methods on their tabular data sets to do predictive tasks. And they want to understand why certain predictions are made. So I research conditional Shapley values as a method for explaining predictions made by black box models. I do this together with my supervisors, Ingrid, Martin, and Kjersti. This talk is going to be based on my second article called Comparative Study of Methods for Estimating Conditional Shapley Values and When to Use Them. I think about that article sort of introduction to Shapley values and summary article for practitioners of Shapley values and how they should apply them. And this work was directly inspired by Chen, who states that conditional Shapley values constitutes an important future research direction that would benefit from new methods or systematic evaluation of existing approaches. And we do both of that in our article. But why is this interesting? Well, as I said, in recent years, a lot of people have moved from using statistical, simple, interpretable models to using more complex machine learning models like projection, pursuit, regression, random forest, boosting, and obviously neural networks. And they often get very accurate predictions, but this comes at the cost of interpretability because these methods have a very complex decision-making process, hence the term black box models, which can be a drawback in a lot of high-risk environments where you want to understand why certain predictions are made. So one of the goals of explainable artificial intelligence is to develop post hoc explanation frameworks to open up the black boxes and make the decision-making process more transparent by quantifying the inputs features effect on the outputs. This can help developer debug the model, find biases in the model, and provide explanations required by legislation. There exist many types of explanation frameworks for different data types and based on what you want to do with your explanations. But one of the most used ones are Shapley values or conditional Shapley values, which is a model agnostic explanation framework with local explanations. Model agnostics means that we can explain the prediction fx star for any kind of model f. And local means that we do so for a specific feature vector, x star at a time. And Shapley values do so by providing important value scores, phi j star for each of the features. So as Idris talked about, Shapley values are a quite old concept, and it arises from cooperative game theory back in the 1950s. And it was a solution concept of how to fairly divide the payout of a cooperative game V onto the M players based on 4 fairness axioms. These axioms are based on that a player that doesn't contribute should get a value of 0. If you have 2 players that contribute equally, they should get the same value. And in the example of Idris, that the whole cake should be divided onto the players. In explainable artificial intelligence, we treat the players as the features, x star, and the payout, which we want to distribute onto the players, will be the predicted response fx star. The game will be based on the predictive function f, but it will not be directly f, but I'll come back to that very soon. Furthermore, a little bit notation, let matcal M be the set of all M players. And we consider coalitions of this matcal M set, so a subset. And note that there is an exponential amount of these. It's 2 to the power of M different possible coalitions. Then Shapley showed that the Shapley value or the importance of the jth player or feature is a weighted sum of the marginal contributions of adding feature J to coalition S, summed over all possible coalition S So this is a very big sum with an exponential amount of terms. But to compute this, we have to define what our gain, our value function, or what we call it, the contribution function is. Idris talked about Shapley effects, then he defined one type of contribution function, but we use the one proposed by Lindberg and Lee, so what's called SHAP, and they define the contribution function to be the following. So they let the contribution function be the conditional expectation of our predictive function, predictive model, condition on only knowing the features in collision S. So here XS is a subset of the whole input X, and XS bar are the features outside the collision S. And note that Lindberg and Lee were the ones who popularized SHAP, and I think this paper has like 15,000 citations at the moment, so it's a very popular explanation framework. And yeah, and one of the reasons why is also because of the desirable property here with the efficiency, which we talked about earlier, that the whole cake gets divided so that the predicted response can be decomposed into the sum of the Shapley values. There exist two paradigms for estimating this contribution function. And in the first one, we use Monte Carlo integration, because then we can approximate the contribution function by the empirical mean if we first generate the Monte Carlo sample XS bar. But for this to be accurate, we need to generate these samples from the conditional distribution of the unknown features, so XS bar, conditional on only knowing the features in the subset S. And then we send it through the predictive model F, and then we take the average of them. So we need to generate these Monte Carlo samples in this paradigm. In the other paradigm, we can note that for this particular game, we note that this quantity right here is the minimizer of the mean squared error loss function. So we can technically fit different regression models to the mean square error loss function and use that to estimate the contribution functions. This has to be done for each collision S, and I'll come back to some drawbacks of that. So here, just to give an overview of the whole setting, so explainable AI, we go down to Shapley values, which we now have divided into two paradigms, and then we have different methods to estimate them. But some of these methods have similar characteristics, so we have combined them into different method classes. So I will give a short introduction to the different method classes. Lindberg and Lee, those who popularized SHAP, they assumed feature independence because of computational problems, because it's quite difficult to generate these Monte Carlo samples that actually follow the conditional distribution. So they assumed independence because then they can generate the conditional samples, or not conditional, but the Monte Carlo samples, but just sampling from other observations in the training data. But then you break the dependency between the different features. So, and that is bad if there's actual dependency between the features, of course. So an idea to try to remedy this is to only sample Monte Carlo samples from observations in the training data, which is similar to the one that you're trying to explain. This was proposed in Olsen et al., who's one of my supervisors. Another idea is to assume some parametric distribution, that X follows, for example, the Gaussian distribution, because then it's very simple to generate the Monte Carlo samples. In this work, we also include the Gaussian copula and the multivariate Berge distribution and generalized hyperbolic. But if you're not able to make a parametric assumption because the data is far from Gaussian, for example, one can use one of these non-parametric generative methods. For example, Radlmeyer, they propose to use conditional inference trees, but then they have to fit one of these for each collision. And in a previous work of mine, we used a variational autoencoder with arbitrary conditioning, which could model the dependencies for all collisions simultaneously. So then I go over to the other paradigm, the regression paradigm, where we want to use regression. We divide it into two different method classes. In the first one, which we call separate regression, we call it separate because we train one regression model for each collision. So for each collision, we generate the corresponding training data. So where the features are the conditional features that are known, and the response, which we want to predict, is the output of the predictive model. So then we can just fit the regression model, GS of XS, by minimizing the mean square loss function to this training data, and that will approximate the contribution function. In this paper, or in this presentation, I considered these 5 regression methods. So linear regression, generalized additive models, projection pursuit regression, random forest, and cat boosts. But this is a drawback because remember there's 2 to the power n different collisions, so it takes quite a lot of time to train all these methods. So another idea that has been proposed is to train a single regression model, G, that works for all collisions simultaneously. This was first proposed by Fry, who limited their setup to neural networks. We have generalized our setup such that any regression model can be used. And the main idea here is that you augment the data such that you combine all of these training data sets for the different collisions into one giant training data set, where we have like an augmented representation XS tilde, which contains information both about X and S. And here we use the same methods as above, but also include the neural network proposed by Fry. But that was a vanilla neural network. So we also introduced Olsen version, which is a neural network that contains skip connections and batch normalization and stuff like that. So now I've gone through all of the different methods here. So I'll just say a little bit about some results, because this was a comparative study. So we did a lot of simulation studies for different setups. And I focus on just one at the moment, but the results were generally quite similar. So we generated a training and test data set of 1,000 and 250 observations, respectively, where the features are generated from a Gaussian distribution, where the covariance between the ith and jth feature is given by rho to the absolute power of I minus j. And we look at different dependency levels from 0, which means independence, to 0.9, which means quite high dependency between the different features. The response is generating according to this function right here, where epsilon is a noise term, and f true is given by this, which means that we send all of the features through a cost function to make them nonlinear, and add some nonlinear interaction terms between the first 4 features. And in this case, we fit a predictive model of which is a GAM with splines for the nonlinear terms and tensor product smooths for the nonlinear interaction terms. Here, as Shapley values is a model agnostic estimation framework, any kind of predictive model could be explained here. We evaluate the different methods by looking at the mean absolute error between the true Shapley values and the estimated Shapley values, averaged over the features and the test observations. I just want to make a note that for real datasets, we don't know the true Shapley values, but as this is a simulation study where we know how the features are generated, we know how we know the true conditional distribution, so we can compute the true Shapley values. So here we look at some of the results. Here we look at the mean absolute error for the different test observations, where we have ordered them based on the overall mean absolute error. So a lower value is better. And in the different facets, we see the different dependency levels. So in general, we see that making a correct parametric assumption, so the yellow methods, the coupler, Gaussian, and generalized hyperbolic, which are all able to model the Gaussian distribution, perform the best. The second best method class is the generative method class, the green one. While we see, for example, that the independence approach, the red one, performs very well when there's no dependency between the features, but it performs very bad when we increase the dependency. Furthermore, we see that regression methods, so in light blue and dark blue, they are relatively bad when there's low dependency, but becomes gradually better when we increase the dependency. However, note that there's a lot of outliers here, and that's a little bit interesting because a lot of papers just report the overall mean absolute error and they don't talk about the individual explanations. But if you take a look at this plot down here and look a little bit more into it, we will see that that's the same plot in the top left here. And in the in the bottom row here, we have plotted the 250 test observations for the different methods. So here we compare the GH method with the Gaussian. And the point here is that it's the same test observation which are difficult for all different methods. So meaning that this dot over here is likely to be a dot over here too, meaning that it's more the data observation which is difficult to explain. And to understand what data observation that is difficult to explain, we have colored the different points here. And we have colored them based on the Euclidean distance from the observation to the training data center. And we see a gradually increase from dark blue to brown, where brown means that it's a test observation which is far from the center of the training data. This should not come as a surprise that if you don't have a lot of data in that region, a lot of training data, then a test observation in the outer part of the training data will obviously perform worse. But this is something that's not really discussed in the explainable AI field, and that can be quite bad because you want to explain your prediction on a local basis. So you need to have more trust in the individual explanations. But it also depends on if you're looking at precise Shapley values or if you just want to get a rough estimate of which of the features that are important. So here I have 3 different test observations with different responses. And my main point here is that, of course, in the different colors, it's the different methods. My point here is that even if the methods are not exactly at the right height as the true Shapley values, they can pinpoint you in what are the interesting features, and then you can use that for further analysis, or we might even use that to build an interpretable model. Just want to say one small thing here is that it's very time consuming, but it's sort of split differently between the Monte Carlo methods, which are easy to train, but they use a lot of time in generating the Monte Carlo samples and predicting the contribution function. This is mainly because the F function is very expensive to call in this example. While the regression models, they are very expensive to train, but once you have trained the regression models, they are very easy to use. So if you consider a practitioner Shapley values who sits in a bank and need to create an explanation for a customer immediately, then the regression models would be beneficial. I just want to say very, very fast that, of course, real-world datasets are not Gaussian. So we looked at different real-world datasets from the UCL machine learning repository with different dependency structures and a different number of features. And we fit the different types of predictive models, so PPR, partial least squares, random forest, cat boosts. And here, since we have to use a different evaluation criterion. So just because for true data sets, we don't know the true explanations. So we used a criterion proposed by Fry et al., which looks at the mean squared error distance between the estimated contribution function and the predictive model. This is advantage that we can actually compare the methods, but the minimizer of this, or the minimum of this evaluation criterion is unknown, so we don't know, we cannot say how good a method is based on this score, but we can rank the different approaches. So here we see the results, a very big table in different columns. We see the different experiments. And one thing to note is that the parametric methods, the yellow methods, are never the best. And this is because none of these data sets are truly Gaussian or Coppola distributed or GH. So it's better to use other methods. We see, for example, that the VIAC, the non-parametric method, is the best for the Avalon all data sets. While for the other experiments, we see that the regression methods are best in all settings. One thing to note here is that in the Avalon Kant experiment, it was the PPR model, the model we wanted to explain was a PPR, and the best model or method to explain it is using the PPR method. And the same if we look at wine, which was a random forest model which we wanted to explain, and then we see that random forest is the best. And the same comes is the case for the adult data set where cat boost was the best. So here we see that it's beneficial to use the same type of regression model it's beneficial to use a similar type of regression model as the one you're trying to explain. But I want to highlight one thing here too. As Idris said, this is very expensive to call and to use Shapley values, because this here took 98 days to explain, I think, how many explanations? 200, sorry, adult 162. So to explain 162 explanations, it took 98 days. So it's not really feasible in all settings, and that is something that one has to work further on. So just to summarize, we did a lot of simulation studies and tried to provide an introduction to Shapley values for new practitioners. And one can obviously extend these investigations into high dimension, determine more robust architecture training processes and hyperparameter tunings for the different approaches. But I also want to discuss one last thing, and that is that trying to explain a model post hoc is not the same as making the model interpretable in the beginning, because then you have to approximate or model what the model is doing. So you get sort of double trouble, and the explanation will vary depending on what kind of game you define. So if I rather had used Shapley effects, which Idris talked about earlier, I would get other explanations compared to what I did here with Shapley values. And that is what I had to say. Here's some references, and thank you very much for listening.
Thank you, Lars, for the excellent talk. So any questions for Lars? Okay, so maybe let me try to ask one question. Could you go back to page 14?
Page 4.
I think you mentioned like the computational performance of among these different methods, but just wonder, did you report like the mean square error or like compare the estimation accuracy of these methods in this table? Is this like a simulation study? Or
yeah, this is a simulation study where I just took the time, reported the time, yes. But this is just based on one repetition. Sorry, I didn't actually get your question completely.
I was just asking, like, have you reported like the estimation accuracy, like the mean square errors?
For the CPU times or for the real Shapley values?
For the real Shapley values.
No, we did not do that. We only reported the mean absolute error in the main article. So we only reported this down here. So yes, that is obviously something we could have done, but we did not do it.
Yeah, I think Andrew also have.
Yes. Thank you. Thanks for great presentations, all four. I have questions for Lars and for previous presentation by Marwan. Not really an expert, but how robust are your Shapley value procedures to what Lars mentioned, presence of outliers, which you nicely showed on the graph? Is there some robustness? You mentioned architecture, how to provide robust statistics, robust methods in such cases, correcting for outliers. Thanks.
That's actually very interesting, because there are papers who use exactly that if you generate data which are outside the data domain, you can actually use that to fool, or you can make explanation that fool, or what I'm trying to say is that you can say that the model is biased in some way, that it's uses the gender feature to discriminate between genders, and then you can use, for example, Shapley values to try to explain that and maybe find out that, oh, it discriminates based on gender. And the point here is that there exist methods that can sort of try to utilize that. If you generate Monte Carlo samples which are outside the data domain, then they can fool the explanation framework to say that, oh, the model is not discriminative, but it's actually discriminative. So there are people working on making these methods more robust. But yes, yeah. Idrisi, do you have something to add?
Yeah, sure. So even in our case, the one that I presented, where we're not interested in a particular prediction, but rather on the variance of the output, using like the thing that we mainly use in order to estimate the conditional expectations and then the variance of the conditional expectation are nearest neighbor procedures. So you can see them as like a non-parametric way to estimate them. But the thing is that they're inherently not robust to outliers. But in the field of XAI, for explanations, so when we say explanations, it's trying to have a decomposition of a particular prediction. There's been some work, I think, by a PhD student whose name is Selim Amoukou, who studied, if I recall correctly, he found, it's a really recent paper, but what he did is that he constructed like balls around the particular data point, and then used the samples that were in that ball in order to have estimations, which would be a way to reduce the outliers, for instance, in the data. Maybe I can find the reference.
Yeah.
Thank you. Thanks.
You're welcome.